When you think about it, atoms have a lot in common with us. Some are kind of picky, some are easygoing, and some are just plain hungry. We're going to talk about that hunger today, an atom's appetite for electrons.
Right? It's a fundamental question. Why are some atoms, like the halogens, practically desperate to snatch an electron from somewhere else, while other atoms, like the noble gases, just couldn't care less, and some even actively refuse them? What's behind this huge difference in behavior? Well, that's what we're here to unpack.
To get to the bottom of this, you really only need to understand two possible outcomes. Two, let's call them energy stories, that happen when an electron meets an atom.
Okay, so the official textbook term for this is electron gain energy. And yeah, it's the energy change that happens when you add an electron to a gaseous atom. But honestly, a much better way to think about it is just as a number that tells you how keen an atom is to get that new electron. It's basically a scientific measure of its appetite.
So, those two stories I mentioned, they're called exothermic and endothermic. If an atom is really keen on getting an electron, the process is exothermic. It happily accepts the electron, releases energy, and becomes more stable. We show this with a negative sign. But if the atom is not keen, you have to literally force it to take the electron. That requires adding energy, making it less stable, and we show that with a positive sign.
So, here's the key takeaway. When you see a negative sign for electron gain energy, think of a happy atom. It's so thrilled to get that electron that it actually gives off energy, kind of like a sigh of relief. It's settled into a more stable, lower energy state. That negative sign is a good sign. On the flip side, a positive sign means you're dealing with an unwilling participant. The atom does not want this electron. It's already stable, and adding this new particle would mess everything up. We have to pump energy into the system just to make it happen, and its overall stability actually goes down. So, let's talk about the superstars of this story. Who has the biggest appetite in the entire periodic table? Who are the champions of electron gain? Just look at this number, negative 349 kilojoules per mole. That is a huge release of energy. This number belongs to chlorine, and it basically screams, I really, really want an electron. It's a signature of an atom with an absolutely massive appetite. So, what makes chlorine and its family, the halogens in group 17, so incredibly hungry? Well, it comes down to two main things. First, they are just one single electron away from achieving the perfect, super stable electron setup of a noble gas. Gaining one electron is like winning the stability lottery for them. And second, their nucleus has a really strong positive charge that powerfully yanks that incoming electron towards it.
But, it's chemistry. So, of course, it's not always that straightforward. Just when you think you've got the pattern figured out, the periodic table throws you a curveball.
Okay, so here's our first big mystery. Based on what we know, a smaller atom should have a stronger pull, right? The nucleus is closer to the edge. So you'd expect tiny little fluorine to have an even bigger appetite than chlorine, which is right below it and bigger. Makes sense, right? But then you look at the actual data. Chlorine, the bigger atom, releases more energy. Its value is more negative. Negative 349. Fluorine is only at negative 328. The bigger atom is actually keener. So what on earth is going on here? And the answer is actually kind of funny and a little bit counterintuitive. It turns out, in the world of atoms, being too small can actually be a problem. Think about it like this. Fluorine is so tiny that its outer electrons are all crammed into a very small space. It's like a crowded elevator. So when a new electron tries to squeeze in, all the other electrons, which are also negative, push back. There's a ton of repulsion. That repulsion weakens the overall pull, making its appetite just a little bit smaller than you'd expect. Okay, so now let's go to the complete opposite end of the spectrum. We have atoms like beryllium, magnesium, and nitrogen. These guys don't just have a small appetite, they have zero appetite. In fact, they'll actively fight you if you try to give them an electron. And why is that? Well, it's because they're already perfectly happy and stable as they are. Beryllium and magnesium have a completely full S subshell. Nitrogen has a perfectly symmetrical half-full P subshell. These are really stable arrangements. Adding another electron would just mess up that beautiful stability. It's a classic case of if it ain't broke, don't fix it. All right, we've talked a lot about gaining that first electron. But what if an atom tries to get greedy and go for a second helping? Does the story change? Oh, it absolutely changes. Let's just walk through the logic. After an atom gains one electron, it's not neutral anymore, it's a negative ion. Now you're trying to bring in a second negative electron. And what do we know about two negative charges? They repel each other, big time. You're no longer dealing with attraction. You're fighting against a powerful force pushing you away. You have to add energy to overcome that repulsion and force them together.
And this brings us to a really simple, unbreakable rule in chemistry. The process of adding a second electron is always endothermic. It always costs energy. Always. There are no exceptions to this one.
So, we've seen the super keen atoms, the totally uninterested ones, and even some surprising plot twists. Let's pull all these threads together and look at the big picture.
Really, the entire story of electron gain boils down to one word: stability. If gaining an electron makes an atom more stable, like it does for the halogens, then energy is released. It's exothermic. But if gaining an electron would decrease stability, like for nitrogen, or if you're fighting that massive repulsion to add a second one, then you have to put energy in. It's endothermic. That's it. It all comes back to that fundamental drive for stability.
And that leaves us with a final thought. If this one simple idea, the drive for stability, can explain an atom's entire appetite for electrons, what else can it explain? Think about chemical bonds, reactivity, the energy of reactions. How many other behaviors are secretly being guided by this exact same principle? As it turns out, pretty much all of them.